there are different frequencies of light and so on for different things. Like sometimes you want to use some LIDAR that can get through water a little bit. So you use blue wavelengths. More typically, red wavelengths are used. There used to be, I don't know if it's still here, a free hour-long short course on LIDAR if you want to take it. So what do you see here? Well, we can see what's interesting about this particular picture is we can get some water penetration here. It's not typical for LIDAR because most LIDAR, for various whatever reason, is using infrared or red near infrared wavelengths, which do not penetrate water. But so here you can see you can make out individual buildings here. This kind of shading of orange and yellow and green, probably you recognize that already as ground level elevations. So that's the digital terrain model. One of the things about LIDAR is we can detect both the built surface and the vegetated surface environment and the ground levels under the right conditions. Just to review here, passive remote sensing is based on the sun. So the sun beams its beneficent rays down to the Earth. The rays, the spectrum interacts with land features like trees and water and the ground, and then beams these back up to a sensor system. The sensor has got detectors on it in different wavelengths, and those different wavelengths capture a data stream that's then beamed down to a ground station, and then underneath here is a fiber infrastructure that gets it out to the world. So that's passive. Active remote sensing is based on energy being broadcast off the satellite or off the aircraft or off the drone. And those are laser pulses. They're big energy power generators that push the energy down to the Earth and then watch what happens when it comes back. And so the interaction is that we call that active remote sensing. And again, it goes down to a ground station and off to the world. And as I mentioned, LIDAR is light detection and ranging. And I like this picture because it shows this swath. Here's a swath of laser beams that are going down to the Earth, interacting and coming back up to the sensor. And behind the aircraft, you can see it's mapping elevation using a color ramp that we're already kind of familiar with. As it moves across the landscape, it collects in these swaths that have a certain width to them, depending on the height of the sensor and the type of sensor. Typically, you get very, very high resolution, like nowadays inches of resolution. I used to say here less than a meter, which was awesome at the time. You get spatial resolution, so you can see very, very small features, but you also get high elevation resolution. And so you'll see what the implications are for this. How many people are involved in archaeology? Oh, I don't have my Zoom open. I'm going to open up Zoom here real quick. Anybody doing archaeology on Zoom? Well, LIDAR has become a very, very big deal in archaeology, and especially in Mesoamerican archaeology of recent times. Now, there's this concept of multiple returns. So the lasers don't just give a single bounce back, they give back multiple bounces. And we'll talk about what that means in a moment here. The active remote sensing means that the platform, the aircraft here, is in motion. So that adds some dimensions of complexity. The motion is, of course, forward, and if it's doing turns to the side and up and down motion. So those are the three GPS angles of X, Y, and Z. But in addition, the aircraft is changing its orientation. The wind is blowing. So you've been in an aircraft. When the wind blows, the aircraft shifts a little bit. When it's making adjustments, when the wind blows and it shifts to stay on course, the lasers are going off in a different direction, right? So it has to keep track of that through what's called an inertial measurement unit, an IMU. And the IMU is constantly tracking the changes in pitch, roll, and yaw of the aircraft as it's flying, as the lasers are beaming around. Okay, I thought you'd seen something shocking. Oh, okay, not too shocking. Good. It's like, what's that gorilla doing in the hallway? Okay. So the inertial measurement unit is recording all this. It's all being captured at the same time. The lasers are being recorded from the landscape. So there's a lot of processing going on. And in addition to get very high accuracy, there's often a ground global positioning system base station that helps these X, Y, and Z values retain accuracy. So there's a lot of heavy technology in this, which is why LIDAR has tended to be very expensive. Here are the two kinds of surfaces that we get. We get we get a digital elevation model. Subsets of that, the way I think of it, are the digital terrain model of the ground and the digital surface model of the built or vegetated surface. Now, you can see this building here. There's a little story embedded in here, which is in these little curves down here. It's a lot of times the lasers don't get right into the corner. In fact, they can bounce off those walls and cause some distortion. So there's some complexity in getting the exact location of the corners of the roof down to the ground. But we do what we can. The main thing is there are two different surfaces we can derive here from the different returns. You've worked with NED, so here's an example of NED in the background here, the National Elevation Data Set, and then LIDAR topography in the foreground here in this interior area here. And you can, this is showing schematically how much more detail, more resolution, more texture, more topography, more features. Right here, exit ramps and entry ramps on a highway exchange, for example, and some various corrugations we'll see in a moment here about glacial striations on the land surface. And this is just looking at the bare earth, as we say, the DTM in this case. Higher resolution does bring with it a lot more cells, a lot more pixels, a lot more data, really much bigger data files. So, it's kind of why we put this course of LIDAR into the third of the three courses, because by now everybody's pretty much familiar with data management and knows about kind of how big and small data sets should be and shouldn't feel intimidating. A lot of people, when they start with LIDAR, it's like, oh my God, these files are so huge. I don't know where to put it. I'm running out of space. I can't process it. I don't have enough computing power for it. So we do start to push the limits with a lot of people's capabilities. Here's a use case for flood forecasting. So on the left side here, we've got 10-meter digital elevation model and a 7-foot contour interval. You could see the floodplain here pretty well. On the right side here, we can see a lot more detail in the channels, a lot more specifics about where floodplain is and where it's a little bit elevated with this vegetation. This is a very topical way of thinking about a lot of the rivers on the Olympic Peninsula, where you've got gravel bars that are really important for fish habitat that have different levels of vegetation on them. And so we've been doing with the 10,000 Years Institute, for example, we've been increasingly doing work with them using drones to simulate LIDAR. Another story there. So that's a use case for flood forecasting. Here's a use case for forest stand characterization. So we can get the bare earth here in the middle. The first return, I know you don't know what that means yet, but let's see. I'll wave my arms and then we'll get to it in detail. The first return comes off the tops of the trees. So that's what it maps as the digital surface model, or the tops of the buildings, which there are none of them here. The last return comes from the ground. And so that gives you the bare earth. So what can we do? We can subtract them. Well, you know about raster algebra a little bit at this point, that we can use these raster layers to create surfaces, and then we can actually run a simple arithmetic on them. And now we can characterize forest stands here based on the height of the trees. The height of the trees as expressed on top of the first return on top of the last return on top of the surface. This is geomorphology, and in this area here, we're looking at glacial surfaces on Bainbridge Island, and so here's a big yellow landslide feature with kind of a toe of debris around the outside of it here. I don't know what this blue represents, but let's see here. The glacially fluted surface, GF. So they're showing some of these striations here. There's another example that's a little bit better here. That's showing where the ground surface was scraped by ice and creates some almost indetectable surface variations, but LIDAR can pick them up. And here's on the Bainbridge Island was discovered the Seattle fault zone. How many people have been up to the Burke Museum? Have you visited the Burke Museum? How about on Zoom? Anybody? Burke Museum is awesome. It's the University of Washington's Natural History Museum. And anyway, they have a lot of science happening there. And so they went out and dug trenches. UW went out and dug trenches to discover the Toe Jam Hill fault scarp. And they could measure it on the ground by looking at sediments and very, very fine variations at the edge of these trenches. One of the things they see are little mushrooms of water displacement. When the earthquakes happen, the soils get squeezed, and they're little mini volcanoes, like half an inch large, that pop out of the squeezed sediments. The fluid pops out, and they can see that when you dig the trench. So they were doing field work to dig trenches, and then they could see it here on the LIDAR. And even though it's so subtle, you can't really see it on the ground, you can see it on the LIDAR. And that applies to archaeology here as well. Here's landslide risks after the Oso landslide. And so the LIDAR was able to show this big lobe of the at-risk area, and then the current headscarp of the slide. This is from the Seattle Times in 2011. So when they looked at the LIDAR, they found out there were a lot of other artifacts of slides that they could see happening over this same region. So this is a whole slide-prone area, all struck within the past 14,000 years, as it said. Here's flood. So one of the big challenges for FEMA, FEMA is a challenge now to exist, but before that challenge, FEMA's purpose largely was flood zone insurance. And so they needed to have a way to say, hey, your house is in a flood zone or it's not. And that required a lot of delineation, hired a lot of people looking at stereograms, looking at aerial photography, and manually drawing floodplains. So what they've been trying to work on here in this case, in this use case, was, can we use LIDAR to delineate floodplain boundaries? And the green is LIDAR derived, and you can see it's got, the red was drawn by hand, and that was FEMA's baseline, let's say, and the green is just a good deal more nuanced here. You can see it roughly agrees, but shows some of these little tributaries and little embayments that might be more meaningfully representative of the precise boundary of the floodplain. And if it could be done reliably, it would be able to automate some floodplain definition. So these are all use cases, and here's the really fun one. This area of Roman era roads in England around 65 AD, or Common Era. There's a good article here. I hope it still works. I'm going to click through to see if it still is alive. Lasers reveal lost Roman roads. Okay, it's still there, and there's the picture I'm showing. When I see these articles, I always clip them, and then I want to look at them later. And I usually do, but anyway, I love the pictures. So here's a Roman fort. You can see all of this definition out on the ground. It looks like just grasslands, because the vegetation obscures the detail that's buried beneath the vegetation. So there's a lot of work being done. I don't know if people are interested in how many people are interested in the history of Central America, but there's a fabulous book called I might be in here. I'll wait for just a sec. Here were coastal bead makers, and they mounted LIDAR on drones. And when they were looking at the Deepwater Horizon oil spill, they found these rings of oyster shell. And here's what they look like on the drone imagery. So they didn't know what these were, and they went and looked at them, and they discovered that they're shell beads, and they were part of the Eastern North American tribal history of roughly 1,000 Common Era, including the Raleigh Island village of 8,900 to 1,200. And one of the things that's coming out of these LIDAR discoveries is that these cultures were much broader scale, more massive, had more people, more wealth, more infrastructure than what archaeological digs tend to show, because digs tend to find like, here's an interesting site, and you sort of get site focused. And I hope I hope I added in here. Yeah, here it is, The Lost City of the Monkey God. This book is awesome. This is a terrific book about discovery of pre-Columbian Eastern Honduran urban civilization with highways and cities and major groundworks and pyramids, and it's all under jungle. So as they've been discovering gradually with deforestation, isolated examples of artifacts from Mesoamerican culture, they said, well, let's look at this more broadly, and they ran these lidar surveys from aircraft and were able to map large areas of eastern Honduras and begin to understand this very sophisticated lost civilization. It has gory mystery, it has pyramids, it has leprosy, and it's all nonfiction. The spoiler alert, but the scientists get leprosy while they're working in the field, and there's the whole chapter on what all that meant as they were out doing the groundwork in eastern Honduras. And here are some of these Mayan era pyramids that are just so amazing. The amount of technology and building and the number of them and the interactions between them and their cultural centers, really stunning archaeology. Here's a map that I made of the Deschutes River Preserve. This is the only ecosystems. The Olympia Airport's just off to the left here. And so this is, I shaded in the roads with some transparency, and then I got the LIDAR. And what they wanted to see was the character of a basin here. And what Olympia Ecosystems is trying to do, and this is just down near Olympia Airport, as I said, they're trying to get this whole area here to kind of fill in with water to be a artesian or a groundwater recharge zone. And it was a dairy farm for 50 or 100 years. It was abandoned in about the late 90s. They got it about 5 or 6 years ago, and I've been doing work with them. And actually, some of our students here have done theses there and other studies. So basically what I do is I use one of those elevation palettes, and I did what I was showing you before, where I changed the colors around because they wanted to really show the watery areas in shades of blue and green, which meant I had to pick a different color scheme for the above ground, higher landed areas. And here's the Deschutes River coming through here. You can see its channels and how its channels divide and braid and the old oxbows and things. So I'm pretty pleased with this. When I zoom in on that area, here's what you see from these channels. And this is just out of a LIDAR that I got out of the USGS, right? Daniel Einstein of Olympia Ecosystems loved this. It was able to go off and get money and grants and extra land donations because he's trying to show how integral this area could be to the whole hydrology of the Deschutes River and the Deschutes Estuary Restoration Team. And, everybody kind of is on it. So a map, I'm very proud of this as a map that helps us to understand a habitat restoration area that just looks like flat farmer dairyland in real life. Okay, here's a 7-minute video about LIDAR technology. I'm not going to watch the whole thing, but I will turn on enough of it if it'll turn on without me getting through. Here we go. Painful. All right, and I'm not going to have it speak for itself, but I'll stop at a couple places here. You've heard of sonar, and a LIDAR system uses light sent from a laser. So that's what I wanted to see there, right? Here's this pulsing laser, and it's running a swath, as they like to say, similar to making a. Okay, anyway, all right, here we go. How are lasers used to measure trees? So there is the digital surface model in white that is being picked up by the LIDAR data. And there is ground-based LIDAR, but here's this aircraft-based LIDAR and satellite-based LIDAR. And let's look at airborne LIDAR, which is the most common. It's kind of the sweet spot between being low enough to have high resolution, high enough to cover areas, and large enough areas. I love drone LIDAR, but it's still very small project areas. So here are the four parts of the airborne LIDAR system. First, there's the energy transmitter coming out of a port from the bottom of the aircraft, scanning the laser. And it's using either green or near infrared light. And that's because these have good vegetation responses. Okay. Then you've got to know from satellites where the aircraft is at all times, its XY location. And we've seen this before with GPS data. The triangulation of multiple satellites gives you a position. And then pitch, roll, and yaw are the motions which the inertial measurement unit tracks. So we talked about that already. Right. Thank you. They're worried about people getting bored in 4 minutes, right? Or 7 minutes. Okay. The computer, which is not a laptop, is capturing all this information and doing a lot of processing on the fly in the aircraft. In fact, when you look at this aircraft, there's a big computer module the size of this podium here, and then the computer puts all these things together: the laser, the IMU, and the GPS. This is terrestrial LIDAR coming off a ground system. Okay, all right, here we go. The laser is emitting energy and it's bouncing back. I want to get to the returns, and then we'll stop this thing. Yeah, okay. All right, so there's a pulse of LIDAR. It's traveling at the speed of light. So knowing that, you can measure the time that it takes for the LIDAR to come back, divide by the velocity, and you've got the distance. So here's the pulse and the return. And of course, it's based on time. Okay. So there's the first return coming off the top of the tree. So you can measure the travel time. And there's a pulse that comes off the bare earth, the ground. And so from that, we can get distance to the ground. Now, this is looking straight down, but of course, the pulses go off to the side. So there's some trigonometry involved in that. Uh-oh, somebody just left. Okay, so let's see. If you know the altitude of the aircraft and you know the time, then you can figure out what the ground elevation is. If you know the speed of the pulse and the amount of time it took to create the return. So that's the basics. There's a graphic I love here that I just want to get to, which is the pulse going in between the trees. Yeah, now as I mentioned, the aircraft is moving around in pitch, roll, and yaw, so the IMU captures that. Because that's going to lead to some attenuation of the signal. And okay, here we go. Now it's scanning, and in a moment, yeah. So now he's got to deal with the angle of the scans. It takes longer to come from. It takes shorter to have a nadir beam than say an off nadir beam, which takes a longer time to come back. So it's got to figure that out. It's amazing that this works at all, really. And okay, so there's the pulse. There's the time, which gives you distance to the ground, or distance to the response, distance to the reflecting surface. Then it uses the IMU to factor in the altitude and the tilt and the any motions, and then the GPS to precisely capture the location. And we're still waiting to get to returns here. Here we go. Yeah, tree height. All right. Yeah. Okay. Here's the picture I want. There's the first return. So if you get one return, it comes off the top. Now, this is what I like, is the beam kind of shooting through the trees. This is obviously a a cartoon, but where's the aircraft? Come on now. There we go. So there's the beam, right? And it's picking up different things. It's bouncing off the sides of the trees. It's bouncing off the branches. It's bouncing off the tops of the trees. So you get a return. You get a first return here, and you can notice that that gives you a little response peak. Then another return from a branch, another return from another branch, and a return from the ground. And this gives you. So here's your strongest return. If I get that, the return energy is larger to the right on this index, and unfortunately that little subtitle is in the way. Let me see if I can go a little further with it. There we go. So you get kind of a weak return from the top of the tree, another weak return from some like limb or something inside the tree, an even weaker return from some understory, and then you get this strong return from the ground. So the laser can penetrate the vegetation, get to the ground, and now you've got 4 returns to come back. So from that laser pulse, the computer is also calculating these tiny fractions, nanoseconds difference between one pulse and its multiple returns as it comes through the trees. First, second, third, fourth return. All right, that was the concept I wanted to get to, and then from there people are really good at this, can do things to understand types of trees, shapes of trees, and there's even LIDAR that can be worn on a backpack that kind of comes out in front of you. And one of our former faculty had one that he was able to borrow from UW to come and do LIDAR views of the campus. Okay, that was a lot of that. But I wanted you to see that whole cartoon, that whole illustration of the multiple returns, because you're going to work with these returns in the coming lab using LIDAR. Here's another picture of this from Nesbitt Remote Sensing. Same idea here, right? We've got, in this case, 5 returns. A return from the top, a return from a branch, another branch, and then finally the ground return, the last return.
You know how they today?
Yeah, right.
So like it's being shot from the plane at this angle.
Yeah.
It should 90 degrees bounce away from the plane.
Yeah.
But it comes back to it.
Well, it comes back to it, I guess. I mean, I don't know what the physics of that is, and how much dispersion there might be. For example, that maybe enough comes back, but some also disperses out. Yeah.
LIDAR section by plane.
Right. On Zoom, if you didn't hear that, I was asking how long it takes to create a LIDAR layer by plane. I think the Thurston County LIDAR missions take a day or two. And I don't know how much of that is logistics and how much of that is, going back and refueling and going out again. The height is a factor of that. For example, with drones, I know that when we do drone imagery at 400 feet, we have much less time on mission than if we fly at 100 feet. But if you fly lower, you get more resolution. So there are trade-offs all along the way there. Yeah, Kelly.
They overlap.
Right. Very good. Yes. Exactly. They do overlapping passes. Sometimes they do them in a crosshatch, but that's twice as expensive. But what they do is overlap them, and you can often see that overlap in the images because of what Avram is referring to, because the angles are slightly different. There's like edge artifacts, and that's a whole smoothing process where we have to kind of average those multiple passes together. 2 summers ago, we had a local volunteer bring his LIDAR drone to the campus, and he flew the central campus with the drone at, I think, 300 feet. And it was like 9 passes. So, and each of those overlapped, and then we processed those to create one image out of that. Yeah, these are good questions. How about other questions? Well, if you have any questions on Zoom, I'm not looking at my Zoom at the moment here, but if you do, use your microphone, please. Anyone there? My laptop battery is starting to die, so I shut my Zoom view down. So Haley, let me know if anybody has any questions, please, or let Haley know during this lecture. Okay, now water causes some problems. No big surprise there. You know, is everywhere in our environment in one form or another, and um, and the interaction of energy with water is complicated. So you get these like weird, you know, pustules over the water here, which are anomalies or artifacts. So that's, you know, that's a tricky thing. Um, but you can see here, we can detect bridges, we detect obviously blocks and buildings, um, uh, so often you'll get water corrected LIDAR where they've actually taken a, another layer of water that's just polygons from the National Hydrography data set, polygons of lakes, polygons of broad rivers, and just forced a level onto those so that they look flat and don't have these weird artifacts. Uh, we often refer to the bare earth model here. I think this is the same area, is it? It's a little different scale, I'm sorry to say. So you can see this sweep of river here is this sweep here, and this island around this oxbow is this here. The bare earth is not quite bare, is it? Like here we can see all these buildings, this popcorn texture near where my little hand is. Those are lots and lots of buildings. This is probably space-derived LIDAR. But you know, we should see a flat surface here. We do see evidence of the blocks. So like the bare earth processing is not perfect. Sometimes you do see evidence of surface features sneaking into your bare earth model just because it's hard to process them all out. And sometimes that's because you don't get enough density of returns to the ground that the first returns are taking. So like in dense forest, you don't get enough ground penetrations to generate a really good bare earth surface. Okay, why we would use the DSM, the DEM, and DTM. There's a little asterisk there. Oops, sorry, I meant to go back. Okay, well, all right. Yes, okay. So the digital surface model gets used in telecom, aviation, urban studies, a lot of things that involve infrastructure, including vegetation management around utilities. Like everybody knows how California and the utility company there, what's his name? Just went out of my head. But they've been operating in bankruptcy for 15 years because they went to get such tremendous legal exposure from failure to manage their vegetation around transmission wires that led to massive, huge forest fires, right? Wildfires and tremendous loss of property. You know, although that's vegetation, it's really about infrastructure and land use. So digital surface models tend to be about the built environment or also about forestry studies. The bare earth gets used in hydrography. So we're going to do a lab later this spring where we use LIDAR as a bare earth surface and then observe, calculate where each molecule of water, each droplet of water would have to flow based on that LIDAR. And from there, we can come up with rivers and watersheds. So hydrography and watersheds and flow modeling is a use of high precision elevation models that come from the bare earth of LIDAR. Wetlands habitat, terrain stability like landslides, soils, land use, geology, geomorphology, archaeology. And then there's another style here, which is become a bit of a detail. People don't use tins so much anymore. They used to be used a lot for mining and engineering and close range photogrammetry and volume calculations of cut and fill. You know, that's an engineering orientation. For those that are thinking about trying to define a project, here are 1,000 GIS applications, many of which touch on LIDAR. But for example, archaeology, lost cities, archaeological survey, antiquities geodatabase, landscape dynamics, site investigations. And from this, let's see if this link still works. Oh, come on, there we go. There we go. Here are literally thousands of potential projects and use cases. So if you're still thinking about your project, this is a good week to look into this. Those of you that might be contemplating different types of projects, cultural heritage or parking availability or fish habitat or hydroacoustics or spawning sites, you know, there's a lot in here that you could you could just peruse and contemplate for your own final project definition. Sources of LIDAR are increasingly plentiful. So this lab, let's see, actually this lab is not taken from the Puget Sound LIDAR Consortium, but the Puget Sound LIDAR Consortium used to be as good as it got. Now there's data also from the Washington DNR LIDAR portal. And I think I heard that they're going to do the whole state this year. So I don't know if anybody has any detail on that. That was geo gossip. So, I should try to find out more about that. There are gaps in this, notably tribal areas who prefer not to be imaged or have their own sources that don't go into the DNR LIDAR portal. Yeah, yeah.
Data, what is the earliest that it started?
Great question. Yeah. Annika's asking, when did this start to be gathered? The Puget Sound LIDAR Consortium was an interesting problem because they were getting, let's see, in November 2010, they had a fair amount of LIDAR, but it was still kind of a little bit locked up behind. You had to contact Harvey Greenberg to get a password, and there was like constraints on it. So that's when it sort of starts in terms of coming into the public domain. However, a lot of the data from 2010 up until 2018, maybe somewhere in that time frame, was not great quality, and they didn't let you have the source, the raw LIDAR. What you got instead was a digital terrain model derived from the LIDAR. You could do a lot with that. There was a lot of really great data there, but it wasn't as primitive as we kind of want to get back to the original data. So you could say reliably for the last 10 years. Yeah.
But is it accessible now?
Yeah.
Like more easily?
Yeah.
than before?
Yeah. Wait, Kelly's asking, is it accessible now more easily? Yes. Thanks to things like the Washington DNR LIDAR portal and the NOAA Digital Coastal Access for LIDAR and the national map, right? All of these have come on since 2018. So when I first taught this course was called GIS for the Third Dimension. Aquarius. No, it was oriented towards elevation, and this slide was the best we had for where LIDAR was coming from in like 2018. Since then, there are these other sources that are coming available, and the LIDAR portal is being updated, and the Coastal Atlas portal data access viewer. I haven't checked this lately to see if NOAA is still able to produce this. Yeah, there it is. So there are links, by the way. All this PowerPoint, when you download it, you can click on the links to get the source. Now, if I can find my way back. And notably, the national map is really, really growing in terms of the 3D elevation program, which was new in maybe 2020. The 3D started to find its way in as a major feature of the national map. And this says up here, oops, sorry. Provides high resolution in the 3D sources. So you can see here, we've got different quality levels, QL1, QL2, QL3. So this is also, as these things evolve, we start then to prize apart which ones are the ones that are best for different uses. So there's a lot of, QL1 LIDAR here, 0.35 meter NPS. Let's see, NPS. I should know what that means. It's got to be some version of resolution. Point cloud 3, these light greens are not as high quality. The middle greens are not as high quality as the best quality here, which is black and or the QL1 green. Less than or equal to 0.35 meters, so a foot resolution, let's say. And some of it's topobathy. We already saw what that means in relation to Finlayson's poster from last week. So Washington State has a lot of QL0 and QL1, which is the best cell size of a half a meter. So, around this area. Now, notice the gaps here, right? The Quinault Reservation, the Nisqually Res, uh, uh, some of these other areas. And the national parks, they have their own schedule if they ever do it at all. Uh, now, LIDAR files are really big. They're huge. So it's hard to move them around over the internet. So somebody at the American Society for Photogrammetry and Remote Sensing, ASPRS, came up with LAZ format, which is compressed LIDAR. Okay, so that's great. Now you can move around files that are like a quarter of the size of what the raw data is. So you can move around 4 times faster. But when they come to us, we've got to do things to decompress them. And so that used to be hard. It's gotten better now that ArcGIS Pro has LAZ to LAS conversions. LAS is the American Society of Photogrammetry and Remote Sensing format. So we refer to them as LAS files. And then LAZY or LAS files are the compressed versions of these. So what you get off the web is coming to you in LAZY files, and then you have to decompress them to make LAS files. So, as usual, now we're looking at like painful data management activities. Here's the USGS LIDAR that I got for making that map of the Ellwanger, or rather the Deschutes River Preserve. So you can see I got 4 frames. There's the airport over here. This is that one I made for the all the ecosystems. And I was able to find those here by doing a search on the national map download. It worked fine. So those of you that were happy getting NED data out of the national map, you can get LIDAR data with not much more effort. You can view the metadata. Here were 4 LIDAR point cloud files downloaded. It's got good metadata generally. But you want to read that. One of the real challenges in metadata is keeping track of feet and meters. The usual, like, it's the gift that keeps on giving, like, oh man, do I have to do this again? It's very easy to get confused, and they can make mistakes in the LIDAR data. They can code it as meters, tell you it's in feet. So, you have to trust but verify. Just one sec here. See if I can get back to Zoom on my laptop here so I can take questions. That's me rejoining. Sorry about that. I had to turn off to conserve my battery because I forgot my keys and my power supplies in my locker. And anyway, enough of that. Here is the old model builder that we built for being able to go through a folder to convert LAS files through an iterator to convert LAS and create output LAS data sets. I don't think we have to do that anymore, but this is just another example of how model builder kind of can help fill in some data management tasks. When you put in your LAS file, your LAZ file, to convert LAS, which is can somebody look up what LAS means in relation to LIDAR? I could do it, but I want to know what the actual words are. The first word has to be laser, right? Anyway, it'll go through everything in a folder. Andy. LIDAR aerial survey. Thank you. Okay. Yeah. All right. Those are LAS files. Thank you. And then when they're compressed, they have a Z on the end. Kind of the idea of WinZip, right? Okay. When we get into the LAS files, now we can see here again covering this area that I made that map for with the Deschutes River in it. Here are the 4 frames. So the 4 frames don't show any data yet until you zoom way in. And then when you zoom way in, and here's what Kelly was talking about or asking about, we've got a little bit of a little boundary thing happening here, right, between the adjacent frames. There's some overlap there. So you're going to create a LAS data set as a GP tool here, geoprocessing tool. Here are the 4 frames. We're going to create a last data set, and it's going to point to each of these. We're going to give it a coordinate system, and it's going to compute statistics, etc., to create one logical frame. So it feels a bit like a mosaic data set. Once we've got that, then we can see, this thing's driving me nuts. We can see each of the different last files and what their rate of returns are. So this one had 18 million first returns and 18 million last returns, and a potpourri of first, second, third, fourth, and fifth returns. Some of them were single returns that didn't generate a first, or rather a second or a third. So you can get that out of the properties once you create your last data set. You can set filters here under last filters, so we can decide if we want to look at all points, ground points, or not ground points, for example, or look at first returns for treetops. So once this is in here, you've got all these tools. This is like super powered DEM is what we're sort of thinking of here. Instead of just looking at one flat raster like we did last lab, we can look at these different levels and layers within the LAS mosaic data set. And then here's what I did one here on the Ho River. So here's a Ho River area, and this is a dozen or so frames. You can see how these all work together to create one last data set. Now, actually, these are 2, 4, 6, 8, 10, 12, 14, 16, 18 frames of data that are off on a storage disk somewhere. And the last data set knows how to point to each of them in order to bring it onto the screen as one logical unit here. And this is a particular ArcGIS Pro format, but any other GIS has to do the same thing, essentially, to create a large enough area out of these multiple large data sets of very high resolution raster. Here's a little bit of what you're going to make if you do the LIDAR lab. This is one of Baltimore's stadiums. I can't remember if this is the football or the baseball stadium. One is the Ravens and the other is the Orioles, right? That would be baseball? That's football. Okay. Okay, Camden Yard is baseball. Yeah, okay. All right, so this is the Ravens Stadium, football stadium. I'm glad somebody understands what's going on here. Oh, are you? Really? Oh, that's awesome. Yeah.
Been there.
Yeah, no, but you don't say it right. You're not from Baltimore. Right. My father was a taxi driver in Baltimore, so I for part of his life. So here's the stadium here's the 3D view, and you can see these, upper stadium artifacts here, these thingamajigs hanging off the upper stadium, whatever that, lights and cameras and fences and all that sort of stuff. I mean, it's tremendous detail here. Along the way, we can also calculate the height of all the different buildings around, and you can see these little marshmallows of trees. Anyway, that's the 3D view of the point cloud. Then this is what you're going to create, which is the areas that are inundated by potential sea level rise. So here is Baltimore with the Ravens Stadium here, kind of isolated on the beach here once sea level rise actually takes effect. And you can calculate how many buildings are going to be inundated. And that's a little bit of the use case of the purpose of this lab. So this is kind of like getting to your end point will look somewhat similar to this. Okay, is that enough about LIDAR? How are we doing on questions and concerns or about the labs? Okay, that is the LIDAR lab. Let me just quickly touch on the alternate lab, which is spatial temporal hexabin mapping. So this is the cartography lab, and you're going to make a map that looks kind of like this. So this is a derived map of 10,000 or so global piracy incidents that have been recorded over the past couple of decades by the U.S. Defense Department. Who knew? The Defense Department has a global piracy events database, and mariners who experience piracy, which could be a threat, which gets a low risk volume, or it could be a boarding or a kidnapping, right? I mean, all levels of severity, but they're all kept in the ASAM database, which is coming from the Department of Defense website here. Now, I've already downloaded this information, but here's their piracy. This is from the I'm on the NGA, National Geospatial Intelligence Agency, military piracy data set here, and you can download a file geodatabase of ASAM, anti-shipping activity messages. Who knew, right? So this cartography lab is going to take those thousands of dots and turn them into a niceified map that shows hotspots, but this is not using heat mapping. I hope nobody in this course is going to represent their thesis, capstone, or research using heat symbols. Instead, you can use aggregation that's rigorous, statistical, and numerical, and that's what this begins to bring you to. So this lab is useful for people who might have hundreds or thousands of observation points, but want to show them in a spatial pattern in a way that's more coherent to the audience than just a scatter of dots on a map. So this is the cartography lab. You'll be summarizing into hexabins, and you'll be learning about some vignettes and symbol layers. Of course, there's a layout at the end, and those who want to see the movie about it, you can go to John Nelson's Adventures in Mapping. His movie is what gave me the workflow to put this together. He does a 12-minute movie or 8-minute movie, and then it takes like 2 days for me to turn it into a lab, right? He's just so efficient. But it's a very fun movie to watch. Adventures in Mapping. Okay, so that's the alternate. For those who want to do analysis, do LIDAR. For those who want to do cartography, do hexabin piracy. And let's see if everything's published here. You did the practicum. We've done the LIDAR GIS overview. Here's the sea level rise. Baltimore. There are the last files. There's the city of Baltimore base data on buildings and roads and so on. And here's the turning point. Here's the hexabin. There's the document. Here's the ASAM database that I downloaded last two years ago. So it's a little out of date, but I think you get the gist. And there's the upload. And here's Haley's poll for open lab hours for her TA hours. So please do respond to that, and then Haley can plan to be available for you. And that's it for tonight's lab. Next week, there will be a dashboard and a generalization cartography alternate. And I do hope to have one of those. The dashboard is oriented towards, I think the MPA students will like the dashboard a lot. So yeah, that's going to be involving historical locations of Olympia. So it's a fairly static concept, but I think you'll still be able to work through the mechanics of creating a dashboard. And next week, I will have my lab hours on Sunday as well as this week coming. Okay. Are there any questions, including potentially on